We use this sequence. There are three principles that we use: off-above, Pali-exclusion, and Huns Rule. This is the first one, the rule of off-above principle. Off-above means building up, and here 1s, 2s, 2p, 3s, you keep going. That's the sequence how you fill the energy levels. So what is electron configuration? Electron configuration, it is the arrangement of electrons around the nucleus in an atom. You can also use this chart like this. Electrons goes from 1s to 2s to 2p, 3s, and then 3p to 4s to 3d to 4p, 4s, like that. There are some exceptions also in D and F block elements. We're going to talk about those. So this is what you follow. So each subshell, you see, there are 4 subshells. This is S subshell, this one is P subshell, this one is D subshell, and you see here letter F. They all have to, this S, P, D, and F, they all have to do with the shape of orbitals. That's how they are named. So for S subshell, each of these subshells, they are made up of set of orbitals, and for S subshell there is one orbital, and one orbital can have maximum 2 electrons. P subshell has 3 orbitals. Now because one orbital can have maximum 2, so how many 3 can have? 3 can have 6 electrons maximum. So again, if one orbital can have maximum 2 electrons, how many can be there in 5 orbitals? 10 max. And in F orbital, 14 max, because there are 7 orbitals. So these orbitals S, P, D, and F, they each represent which subshell they belong to. So you do not have to actually memorize this sequence. As you do write the electron configurations repeatedly, you will know the sequence little bit yourself. And also, depending on the type of subshell being filled, the periodic table is divided into 4 blocks. So when you're working with elements from group 1 and group 2, you will know that you're moving from like 1s1, and then here 1s2, then after 1s2, 2s1, then 2s2. So that is how you're going on and on, adding electrons next. Okay, because it will be 1 electron, then 2 electrons, 3, 4, 5, 6, 7, 8. And here, when you are here on this side of the periodic table, elements from here, you are going to fill, as I said, depending on the type of subshell being filled. Since you're filling the P subshell here, you are going to see the P subshell when you are actually writing electron configuration. And for the middle, you are going to fill electrons in the D subshell, the D orbitals, and at the bottom, F orbital. So you do not have to sit and memorize the sequence. It's pretty easy. It goes straight forward. 1, then 2 electrons, then 3, 4, 5, 6, 7, 8. And here we have some exceptions, that instead we are going to, the 4s energy will be at the higher level. We're going to talk about that when we work on the examples. So here is the sequence. So there are 3 ways you can represent electron configuration. The first way is like writing full electron configuration for ground state. Here, let's say full electron configuration. Yeah, we are working on the ground state electron configuration, not on excited state. So let's say we have an example, 12 electrons. So if we have to write electron configuration for 12 electrons, this element, we are going to follow the sequence from here. You first start filling electrons. In the S, you can have max 2, and then you have 6. So until here, 2 plus 2 plus 6, you have 10. And then you move on, plus 2 will be 12. So you stop here at 3s2 for 12 electrons. So 1s2, 2s2, 2p6, and 3s2. You add 2, 2, 6, 2, add them, 12 electrons. This is a full electron configuration. You just add those superscript. Now if you have to write, the other way of writing is called noble gas notation, or you can say noble gas electron configuration, or you can say shorthand notation, condensed notation, abbreviated notation, because you include, instead of starting from the beginning, what you do, you write down the noble gas from the previous group, from previous period. So here, okay, periodic table. So instead of writing electron configuration for this element, first of all, what is this element? 12 electrons. We look here, 12 electrons is for magnesium. So now I know it is magnesium. So before magnesium, I had neon that has 10 electrons. Neon is the closest noble gas to magnesium. Elements in the last group, they are the noble gases. So here neon is 10 electrons. So how do you write the noble gas notation? Instead of these 10, 2 plus 2 plus 6, you're going to write Ne, and then you write just this one, followed by 3s2. So this is equivalent to magnesium, which is equivalent to 12 electrons, because this one is 10 and this one is 2. Now, other way is to draw the orbital diagrams. Orbital diagrams, or you can say orbital notation. You can just draw simply a line and show electrons at the top. So 1 electron, 2 electrons. So one orbital, we draw one line, or for one orbital, we can actually make a square and then show 2 electrons. Why I'm showing 2 electrons? These arrows represent electrons. The reason I am saying only 2 here, because one orbital can hold max 2 electrons. So here, or you can draw a circle. 1 electron, 2 electrons, either one. So these are the 3 ways. So if let's follow the sequence of above principle. For helium, I have written these electrons. How did I find these electrons? These electrons are actually same as the atomic numbers. You remember, these are all atoms. So neutral atoms, the number of protons and electrons are equal, which is actually the atomic number. So for 1 electron, I'm going to begin from here. 1s. So 1s, but I have only 1 electron. So I'm going to write here 1. Okay, so why am I doing that? Because if you look here, in the s orbital, I can put maximum 2. This is maximum, right? That means minimum can be 1. Similarly, for p orbital, the maximum electrons we can put are 6. However, it can be any from 1 through 6. Similarly, you can put more than 10 in d orbital. However, they can go from 1 through 10. Similarly, for f, they can go starting from 1 depending on how many electrons we need to complete rewriting the electron configuration of element. So those are the max electrons. In s, can put more than 2, p cannot put more than 6, in the d you cannot put more than 10, and in the f orbital you cannot put more than 14. Can you put less than that? Yes, of course. So we are going to see, I'm also going to explain the rules separately. So 1s, here I write 1. So this is the electron configuration for hydrogen. For helium, there are 2 electrons. So 1s2. For lithium, I start from here. Lithium is total 3. So 1s2. And then I go to the next one, 2s. And you said 1. Yes, because 2 plus 1 is 3. Okay, these numbers at the top, these superscripts are the electrons. 1, 1, 2, 2. 2 plus 1 is 3. For beryllium, it is total 4. So again, I'm going to start from here, 1s2, 2s2, and I stop here. 2 plus 2 is 4, and this is my 4 electrons. Boron is 5. So 1s2, I'm again following the sequence, just follow the sequence. 1s2, 2s2, and then the next one is 2p6, but I need to write only 1. Why? Because I am working on boron. If I do not write 1 here, if I write more electrons here, then it wouldn't be the electron configuration for boron atom. For boron atom, this is the electron configuration, 5 electrons, 2 plus 2 plus 1. Now here, carbon is 6, so 1s2, 2s2, so I'm going 1s2, 2s2, and then I need to go until 6, so I need just 2 more. So instead of 6, I'm going to write 2p2. So 2 plus 2 plus 2 is 6, and this is 6. So remember, these are the maximum electrons, not the minimum. Meaning you can't put more than 2 in S, you can't put more than 6 in p orbital, no more than 10 in D, and no more than 14 in F orbital. Okay. Alright. Let's write the electron configuration for calcium. So we are going to follow the sequence from here. So I'm going to start from here, and I'm going to keep going on and on until I have added all my electrons until 20. So I'm writing electron configuration for calcium. How do I know it is 20 electrons? From periodic table. So 1s2, 2s2, 2p6, 3s2. Okay, 1s2, now this is 10, now this is 12. Again I have to move on, 3p6 and 4s2. So add these 10, 12, 18 and 20. I took this sequence. Now we are going to now draw the orbital diagram. For S, we have one orbital here, S, one orbital, P, 3 orbitals. So that's where I am looking at. S, one orbital, S, one orbital, 6, 3 orbitals, S, one orbital, 6, P, 3 orbitals, S, one orbital. 2 electrons, 1 and 2, 2 electrons, 1 and 2, 6 electrons, 1, 2, 3, 4, 5, 6, 2 electrons, 1 and 2, 6 electrons, 1, 2, 3, 4, 5, 6, and then 2 electrons. Now, we want to also write, so this is the electron configuration, this is the orbital diagram, and how about the shorthand notation? Shorthand notation, or you can say the noble gas notation. I'm going to look at my periodic table. Where is my calcium? Right here. I have 20 electrons for calcium. Which is the nearest noble gas to calcium? Here I'm going to look at the previous period, and in argon is 18, which is closest to calcium. We don't just include any atom, we include only the noble gas atom, all right, only from the last group. So argon is 18. So what I'm going to do, instead of writing until 18, so from here until here is 18, and instead I'm going to write AR and then 4s2. So this is, the whole thing is calcium, because it is 20, this is 18, all right, and this is 2 electrons, 18 plus 2 is 20. What else can you tell from here? You can tell the period number. This is the highest energy level. You can say highest energy level, or you can say valence shell, or you can say outermost energy level. All right. So whichever is the highest or outermost energy level is equals to the period number. So what is the period number for calcium? It should be 4. Let's see if that is true. Yeah, this one is 4 and calcium is in period 4. Period goes across left to right. So period number is 4 for calcium. So electrons. Now how about the valence electrons? These valence electrons. What are the valence electrons? Electrons in the valence shell. They are all equal to the group number. Valence electrons. Valence electrons equals to the group number. So here, what is the group number? 2, which is 2A. Since we have divided elements into this periodic table into A and B group, so this belongs to 2A, or you can simply say 2. Right? Okay. You can also write them in energy level diagrams like this. So here I have taken an example of aluminum. Aluminum is 13 electrons. How do I know it is 13? From the periodic table. So when you look at aluminum, which is the nearest noble gas for aluminum? Aluminum is 13. Neon is 10. Again, we don't just include any element. We include only the noble gas from here. Alright. So which is the nearest noble gas to aluminum? Neon. Neon has 10 electrons. So what would you do to write the shorthand notation? Instead of writing this first part here, we write neon. So we don't have to write this part, and we write neon 3s2 3p1. So when you're going to add 10 electrons of neon, 2 electrons here, 1 electron here, you add them, it is 13 electrons. And what's the period number? Period number is same as outermost energy level, which is 3 here. That's the highest level. 1, 2, and then the 3. The 3 is the highest. And the electrons in the valence shell is group number. So it's group number 3a and period number is 3. So you can check that on a periodic table if that is true or not. And you're going to see, yes, it is true. Aluminum, period 3. Aluminum, group 3, which is 3a. Okay guys, so when you're filling these energy level diagrams, you start from here. You can use this. 13 electrons, so 1s here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, like that. Let me explain you each of those principles. So first one, the principle, first rule says, it shows the order by which we are filling the electrons. So here is the order. This is the order I was following. And what else it tells you? It tells you that you have to fill the lower energy orbitals first. So electrons are going to fill the orbitals with the lower energy first before they move on. So if there are 10 electrons, you're going to start filling from here. 1s2, 2s2, 2p6. So you see this is 2 plus 2 plus 6 is 10 electrons, right? How about if I write like this? What's wrong about it? It is still 10. It adds up to 10. 2 plus 2 plus 5 plus 1. These all electrons, these superscripts tells you the number of electrons. They are still 10. And how about if I write it like this? It's still 10 electrons. If you add 2 plus 2 plus 2 plus 4, it's still 10. So what is happening here is this one is correct because this is following both the rules. It is following the order, and also the electrons are occupying the lower energy level first, because here the lowest energy is here. You always start from the lower energy and then you go on and on to the higher and higher. Here, this is the mistake here. What's the mistake here? 2p5. The rule says you have to fill it up before you go to the next one. But however, you see this is not completely filled. It is 5 here. It was supposed to be 6. So this is the mistake here. So this one is incorrect. Okay. Now what's the problem with this one? This is not following the sequence. 1s2, 2s2. We were supposed to fill electron in the 2p, and here it is 3s2. So this is again incorrect. We will talk about the exceptions or the elements that are not following off-work principle later. So these are the mistakes here. We have to follow this. Those are the rules. Okay. Let's. The second principle is Pali exclusion. So what are we working on right now? I'm just going over the 3 principles: Arpa, Pali, and Huns Rule. Second one is the Pali exclusion principle. The 2 things here are that there can be maximum only 2 electrons in one orbital, and the direction of the electron have to be opposite. So this is one orbital. You can't put more than 2 electrons in this orbital, and also their direction has to be opposite in the same orbital. So if there are 4 electrons, when you look at the periodic table, it will be beryllium. Beryllium has 4 electrons, and you write the electron configuration. You're going to follow the sequence. Where is my sequence? Right here. I'm going to start from here, 1s2, 2s2, and then I'm going to stop here because 2 plus 2 will be 4. So 1s2, 2s2. And when you draw the orbital diagram, for s it is 1, for s it is 1. I'm going to write in 2 electrons, 2 electrons. Okay. If I write 1s2, 2s2 again, there is no problem with that. When you draw the orbital diagram like this, or you write it like this, 2s1. Now, what's the difference between these? This is the first one, here comes the next, and here comes this one, the last one. This is correct. This is following both the rules from above. 2 electrons max and opposite spin. This one, 2 electrons max, yes, but there is no opposite spin. See, this is incorrect. They have to have opposite spin. They are in the same direction, correct, and this one is incorrect. Incorrect. This one, 3 electrons. What did we say? That max 2 electrons in one orbital. And here, S subshell, only one orbital. But how many electrons are shown here? 3. So this is the mistake here. Okay, so this one is incorrect as well. Okay, guys. Next rule is the Huns Rule. The rule says orbitals of equal energy are each occupied by one electron before any orbital is occupied by second electron. That looks like so much to understand, but the example will make it easy. Let's take an example with 7 electron. When you look at the periodic table, it is nitrogen, element nitrogen, total 7 electron. You're going to follow the sequence. We are going to go until 7, 1s2, 2s2, 2p3, because 2 plus 2 plus 3 will be 7. Some of you must be thinking, where are those numbers at the top? I have not written them here. You know why? Because that depends how many electrons will be at the top depending on my element. But one thing I know for sure is S cannot have more than 2, P cannot have more than 6. Okay, guys? Alright. So 1s2, 2s2, 2p3. If you make the orbital diagram, 1, 2, s orbital is 1 and 2 electrons. 1, 2, p orbital, 3. So here 3 electrons, 1, 2, 3. So it is total 7. 2 plus 2 plus 3 is 7. How about if I make it like this? It is still same number of electrons, 1, 2, and 3. However, this one is incorrect. Okay, this one is correct. What's the reason? Look at the reason. 2 plus 2 plus 3 is 7, and it is 7, and this is nitrogen. The reason is they are saying if you have orbitals of equal energy, so we are going, these are completely filled, so I'm not even looking at them, I'm looking at these. These are orbitals of equal energy. First, you have to make sure that they are singly occupied, meaning one electron first. So 1, 1, and 1. Each orbital is singly occupied before you pair them up or before you double them. So you can't double them until each one is singly occupied. Okay, so make sure they are singly occupied first, and then you start doubling or pairing them up, pairing or doubling. So that is why this one is incorrect, wrong, right. All right, so at a time only one electron, just remember that. For noble gases, again, noble gases is the last group on periodic table. I want you guys to write the electron configuration for noble gases. I want you guys to make orbital diagram, shorthand notation, show me the highest energy level, the period number, group number, everything. So noble gases, they have full octet, completely filled valence shell. which is also true for helium, but instead generally when we say octet, we are referring to the number 8. We still say that helium has a complete octet, even though it just has 2 valence electrons. The reason we say full octet, because it doesn't have more than 2 electrons. It doesn't need more than one shell. And whatever it's, the outermost shell is completely filled. So we still say complete octet. But if you want, you can say duet, because again, the octet refers to number 8. All right, so you ready? You're going to pause the video and you're going to write, you're going to do 1, 2, 3, 4, and 5 things for noble gases. And what are the noble gases? The last group in the periodic table. Cross check from here. If this is what you have for helium, you did a great job. You have all this information. If you have all this information for neon, you did a great job. If you have all this information for argon, you did a great job. And then the other noble gases. So you can see these noble gases, they are unreactive. They do not have any unshared pair of electrons. No bonding, no loss, no gain of electrons, no sharing. So we are going to talk all that, like when we move to the bonding part, the ions, you're going to learn more here. But for now, you can see there are no unshared pair of electrons. Completely, they are all completely filled. Here, once again, here you go. If you want to take a picture, pause on here for 18. Just try yourself for others. Now let's work on the exceptions to Aufbau principles. Aufbau principle rule. Some exceptions. Aufbau principle. Okay, guys, this one is the Aufbau principle. You're following electrons. You're going like that. Here are some changes when you are here 4s and 3d level for D group elements. And I am taking an example from D group elements, the D block, and I'm going to do, and I'm going to do mainly focus on chromium and copper. They are the one which are usually asked in exams also. So D group, D block elements, they are the one which are actually the rule breakers. You can say they are the rule breakers. Okay, so if you are writing electron configuration of chromium and you look at the periodic table, chromium is 24 electrons. Where is the chromium? Chromium is in the D block in the middle, and so is the copper. They both are in the middle, the transition metals, the D block elements. So if you are going to follow the sequence, you're going to start from here and you're going to go until it adds up to 24 electrons. So you're going to start from here. You're going to write the superscripts at the top. You know that superscripts, the rule is S cannot have more than 2, P cannot have more than 6, D can't have more than 10, F can't have more than 14. Just remember that rule. So if you have to write that, you're going to write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Now add all these and they are going to add up to 24 electrons. Now to save space and time, I'm going to write the shorthand notation. So instead of 10, 12, 18, you know the 18 is argon. I am going to write abbreviated notation, argon, and then 4s2, and then 3d4. Okay. And I'm going to draw the orbital diagram for this one. D is, look here, for the D subshell, we have 5 orbitals, 1, 2, 3, 4, 5. So I'm going to draw 5 orbitals. 1, 2, 3, 4, 5. So 4 electrons, 1, 2, 3, 4. Okay, not this, only 4 electrons. Okay, guys, this is what is expected. And you are going to stop there and you're going to say, Miss, I'm done. But what happens here, there are, because, and I said these are the exceptions to Aufbau principle. So what happens here is this electron from s orbital is actually going to move to the d orbital. And when that happens, what are you going to get? What will happen as a result? You will have instead 4s1 3d5. Okay? One, two, three, 4, and then 5. So this electron from here moving over here. So this is the reality. In actual, this one is the electron configuration. Now why does that happen? Because we tentatively agree that half filled, this is half filled d orbital, that completely half filled or completely filled d orbitals are more stable. So here this completely half filled d orbital is more stable compared to the partially half filled. All right, so this is more stable, and this is what you are going to write as electron configuration when you're actually writing electron configuration for chromium. You have to fix it at the end. And or you can but if you write it like this, 3d5 4s1, this is perfectly fine. No problem. You can write either way. And so this was chromium, completely half filled. All right, let me do copper. Copper. Look at the periodic table, and copper is 29 electrons. We just did chromium. Chromium it was 24, copper 29, and this is from the d block. So you know that we are going to fill the d orbitals here. Okay, so copper is 29 electrons. I'm not writing the full electron configuration to save time. So AR is already representing 18 electrons. So I'm going to start after 18 electrons, and this is 4s2 and 3d9. Now you must be thinking, how did I get that? Again, the same thing. I use this sequence, okay? And until here, until 3p, it was 18 electrons. So I wrote argon for all this, and then I kept moving on, so that I made sure I have my 29 total electrons. So 2 here and then 9 here. Okay, so 18 and then 20 and then 29. This is what is expected. And you're going to say again, Miss, I'm done. But listen, no, we are not done. Why? Because these are the d block elements. These are the rule breakers. So here 1 and 2, here 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what happens here? This electron from here moves here. Now as a result, what happens? You have AR, you have 4s1, and you have 3d10. Now what happened is 1. Now this d orbital now becomes completely filled. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what did we learn? So this is correct. This is the correct one. Okay, not this one. This is the correct one. What did we learn just now? That if it is half filled or it is completely filled d orbital, it is more stable compared to the partially filled. So since this is completely filled d orbital, this one is more stable, and that's why we write electron configuration of copper like this. Or even if you write like this, 3d10 4s1, that is fine. Okay, now let's do the quick learning check. Which element is represented by this one? So what are you going to do? You're going to add this. So let's add quickly. 2 plus 2 plus 2. This is 6, which is carbon. Helium, 2 electrons. This is 2. This is 1. How much is it? 5. and it is boron. This one, neon. Neon is 10 electrons. 10. How do I know? This is 2 and this is 10. That is, I know from the periodic table. And this is 1, which is 11. And this one is sodium. Okay. Right. Just write this for me. What does each one of these represent? 2. This one S and this one 1. If this is what you wrote, you got it. These numbers at the top, they are the superscripts. They represent electrons. This S, it could be S or P or G or F, 4 possibilities, because there are 4 types of subshells. So this letter represents the subshell or the sublevel. And the coefficient in the front, these big numbers, they represent the principal energy level, or you can say shell. And the possibility is 1 through 7, because there are only 7 periods on a periodic table. And that's what you did. Great job. How many electrons are there in the p orbitals of last shell of chlorine? So you're going to look at the periodic table. Look at chlorine atom. And chlorine element has 17 electrons. So you're going to write electron configuration for chlorine. How would you do that? You're going to follow the sequence. You're going to put electrons at the top, and you're going to add up to until they are 17. How do we know what number I'm going to put at the top? I know I can't put more than 2 in S. I know I cannot put more than 6 in P. Alright, so this is the rule I'm following again. S2, P6, D10, F14. But they are the maximum, not the minimum. Alright. So for 17 electrons, 1s2, 2s2, 2p6, 3s2 and 3p5. My question is, last shell of chlorine. So well, this is the first shell, this is the second shell, and this is the last shell. So now I know which one is my last shell. They're asking how many electrons in the p orbital of last shell. This is my p. This is what they're asking. Okay, they're not asking in S, even though they said the last shell, but they're asking only in the p orbital, and p orbital has 5 electrons. So what's the answer? Answer is this one. Okay. Take some time, read all these questions, take screenshot or whatever you want, and then work on these and write down if they are true or false. Just to let you know, if you answered all of them, okay, I'm going to pause. You take the picture. Here you go. If you answered all of them true, that means you got it. Yes, they all are correct. Read all of them, and yes, they are. If you answered all of them correct, true, you got it. Here is the question from the one exception. This is from exception to our principle. Which of these is the correct electron configuration of chromium? So how do we tell the element? What are we going to do? We are going to first make sure that they add up to what is the number for chromium? I'm going to look at the periodic table, and when I look at the periodic table for chromium, it says 24. So I know one thing for sure, that they have to add up to 24. And then I have to keep 3 rules in my mind. What are those 3 rules? Is it following the off-birth rule? Is it following Polyexclusion principle? Is it following Huns rule? Well, we are not even making, I didn't make orbital diagrams here, so no worries about the orbital diagrams. But I did tell you already that chromium belongs to the one from the exception to the off-birth principle, like those rule breakers. So let's see anyway, let's start. 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 1. 21 electrons. Well, I know this is incorrect. Cross it out, because chromium is how many electrons? 24 electrons. We just looked at the periodic table. And guys, when I write electrons, I always put little negative at the top, because electrons are negatively charged. So in most of my videos, you are going to see negative charge on electron, because electrons are negatively charged. And even if you don't put negative, that's okay. Now then you go to the next one. Uh-oh, here is my mistake. Well, this is a mistake here. Why is that? So this is violating Pali exclusion principle. Remember, the rule was One orbital cannot have more than 2 electrons. And here for S subshell, which is only one orbital, it is showing 3 electrons. So you cross this out. This is incorrect. Now go to the next one. 2 plus 2 plus 6 plus 2 plus 6. Okay, this adds up to 24 electrons. All right. Doesn't look bad. How about this one? 2 plus 2, 6. Okay, well, this is 24 as well. Now now my possibilities are this is either this one or that one. Well, these are the rule breakers and chromium is one of them. So I'm going to look at this one, 4s2 and this is 3d4, right? The electron from S is moved to D and this one is my more stable one because D is completely half filled and this one is partially filled. So this is not my answer. My answer is the last one. So which one is the correct answer? Correct answer is number 4. Okay guys, take care. Thank you for watching. Keep practicing. Nothing can replace practice.